Lighthouse Scientific Education presents a lecture in the Molecules and Compound series. The topic? Covalent bonding, including a discussion on polarity. Material in this lecture relies on an understanding of the previous lectures, bonding in overview, and valence electrons, octet rule, and the dot structure. The covalent bond is a very important topic in chemistry. This lecture covers a number of subtopics relevant to a thorough understanding of the bond. It covers a fair amount of ground and can be viewed in parts. We will begin the lecture with a definition of covalent bonding, then cover the basic properties of covalently bound compounds. To build an understanding of how molecules form, we need to look at the roles of valence electrons and the octet rule. A deeper understanding of what is meant by sharing electrons will be given. This is where we will first introduce a process for bringing atom dot diagrams together to form molecular dot structures. There are 2 lectures in this series that expand on that topic. They are called Basic Lewis Structures and Advanced Lewis Structures. This lecture will only use dot structures to explain the other properties of covalent bonding. A discussion is then had on the equal and unequal sharing of electrons, which leads to a fundamental aspect of chemistry, polarity. We will also examine the multiple covalent bond, as well as polyatomic ions. The covalent bond is a form of bonding called the chemical bond. These bonds are within a compound, and they are stronger than intermolecular bonds, which are bonds between compounds. As for a definition, covalent bonds occur between 2 nonmetal atoms that share some of their valence electrons, and they do so more or less equally. Refreshing ourselves with where the nonmetal elements are on the periodic table, we find them located on the right of that staircase of elements, which are colored pink here. As was described in the Bonding and Overview lecture, covalent bonds are formed when the difference in the electronegativity between the 2 atoms is equal to or less than 0.4. If you are uncomfortable with this point, it is worthwhile reviewing the role of electronegativity in the Bonding and Overview lecture. Covalent bonded compounds are called molecules. Molecules are a subset of compounds. All molecules are compounds, but not all compounds are molecules. One often sees a line drawn between 2 atoms in a chemical formula. This indicates that there is a covalent bond between the atoms. Another important feature of the covalent bond is that the orbitals containing the shared electrons overlap. That is, orbitals involved in a single covalent bond not only touch, but to a small degree they merge. The double and triple covalent bond have a slightly different form of overlap. Overlap is commonly shown in cartoon form by drawing the atoms as circles and having the circles of bonded atoms touch to a small amount. The shared electrons are drawn within this overlap. More on this topic when we get to the section of sharing. Just a note on orbital overlap. If the student is asked to understand orbital overlap in more detail than is covered in this lecture, a deeper explanation, especially concerning double and triple bonds, can be found in the first section of the Advanced Covalent Bond lecture. Be sure, though, that you need to understand this material to that degree before viewing the advanced lecture. Returning to this lecture, a particular form of the covalent bond is the polar covalent bond. It too occurs with the sharing of some valence electrons between 2 nonmetal atoms. But the sharing is done unequally. The shared electrons spend more time around one of the atoms, a topic covered later in the lecture. Polar covalent bonds are formed when the difference in electronegativity between the 2 atoms is between 0.5 and 1.9. What distinguishes covalent from polar covalent is the difference in electronegativity. 0.4 or less is covalent. A polar covalent bonded compound is called a molecule. Since it is a covalent bond, a line between atoms indicates the presence of a bond. and the orbitals of the shared electrons overlap a bit. Same drawing mechanism for distinguishing the overlap between the two atoms. Dots representing electrons are put in the overlap. On to properties of molecules. Remember, when we use the term molecules, we are specifically referring to covalently bonded compounds. Beginning with physical properties. Molecules tend to have low melting and boiling points. They form relatively soft solids, and that is soft as compared to ionic and metallic compounds. They are generally insoluble in water. There are some molecules that are slightly soluble. Soluble in this context means dissolved in water. Importantly, the solubility of a molecule increases with the number of polar covalent bonds. Another property used to describe compounds is their capacity to carry electricity. Molecules are considered non-conductors because they are not good at carrying or conducting electricity. And as we saw with solubility, conductivity increases with the number of polar covalent bonds, although the increase is relatively small. Return to this section after viewing the properties of ionic compounds. Compare and contrast their properties to those of molecules. It gives the properties some perspective. Since a covalent bond is the sharing of valence electrons, it is worth our while to revisit the electron dot diagram. If you feel that you have a good grasp of the valence electron dot diagrams, move on to the Octet Rule for sharing valence electrons. On the other hand, if at the end of this review of electron dot diagrams you are still unsure of how they are determined, go back to the valence electrons, Octet Rule, and dot structure lecture for a more thorough description. A brief review of the process can't hurt though. Listed here are the first 18 elements by atomic number. Added is a column that gives the number of valence electrons for each element. Every dot structure will start with the element symbol. We will use a generic element symbol E as a demonstration. We will say that it can hold up to 8 valence electrons. Around the symbol are what can be considered as 4 equal energy orbitals placed one per side. Temporarily, we will use boxes to designate the orbitals. Hund's rule limits these orbitals or boxes to no more than 2 electrons. We can generate the Hun rule on the diagram by dividing each box in half. There are now 8 half boxes. Dot diagrams are constructed by adding the valence electrons as dots to the boxes, but we do so in a particular pattern. Starting at the box at the top and moving clockwise around the symbol, dots are added 1 dot per orbital. No pairing yet. Each orbital gets 1 electron before pairing. After the first 4 valence electrons have been added, assuming the element has more than 4, begin by pairing the dots, using the same pattern of starting at the top box and moving around clockwise. Oh, and we don't really use boxes. We will quickly move through this table and show that we understand the process of assigning the correct orientation of dots around the element symbol. We will focus on elements that can make covalent bonds. Starting with column 1 or 1A elements. The only element in this column we need to concern ourselves with is hydrogen. It has 1 valence electron. By convention, a single dot is added to the top of the element symbol. We now skip over to column 3A or column 13, the elements boron and aluminum. Their 3 valence electrons go in a clockwise manner around the symbol. Carbon and silicon are column 4A or column 14 elements, and their 4 valence electrons are assigned to 1 per side of the symbol. The column 5A or column 15 elements, nitrogen and phosphorus, have 5 valence electrons. The first 4 of the 5 valence electrons are assigned in the same manner as that for carbon and silicon. That 5th electron is paired at the top of the symbol. Pairing also occurs with column 6A or 16 elements. We see that oxygen and sulfur have 6 valence electrons. The halogens, fluorine and chlorine, belong to column 7A or 17. The first 4 of their 7 valence electrons are added in a normal pattern, with valence electrons 5, 6, and 7 pairing. And finally, the column 8A or 18 noble gases, with their full set of valence electrons. The only other element to concern ourselves with is helium. It has 2 valence electrons, which are both added to the top of the symbol. Helium only has a 1s orbital, and this arrangement is considered a full set of valence electrons. A final point needs to be made before asking why valence electrons and dot diagrams are so important in understanding covalent bonding. And that point is about the orientation of dots around the symbol. Since there really isn't a top and bottom to an atom, the pattern of adding dots starting at the top is not a physical reality. We are not limited to where we start the pattern. Take the dot diagram of nitrogen, for example. Specifically, take the 5th electron, the one that pairs. When we start the pattern of assigning the dots with the orbital on the top of the symbol, we have the preferred orientation, like this one. However, the first dot can be placed in any of the other 3 orbitals, generating 3 equivalent dot diagrams. That 5th paired dot can be on any side. This may not seem very significant, but when we start building dot structures, we will be choosing the most convenient of such orientations. And it's worthwhile pointing out that we are free to change orientations, and that in doing so, we are not altering the dot diagram. It's time to bring up the other important feature that helps clarify covalent bonding. That is the Octet Rule. It says atoms with 8 electrons in their outer shell, and we're talking about s and p orbitals, are the most stable. Remember that 8 comes from filling the s orbital, 2 electrons, and the p orbitals, that's 6 electrons. A more detailed explanation of the Octet Rule is given in the Valence Electrons, Octet Rule, and Dot Structure lecture. It is helpful sketching out a model of a molecule consistent with the Octet Rule, because covalent bonding are going to generate full outer shells for the atoms involved, and it is a common way of demonstrating the bonding in molecules. Why is it that bonding helps generate full outer shells? Well, in a covalent bond, each atom gets to count both electrons in that bond towards its fulfillment of the Octet Rule. More on that momentarily. Back to the rule. It mostly applies to elements in the 2nd and 3rd rows, and it doesn't hold for row 1 elements. A duet or 2 rule can be used for row 1. We can build a sketch of the model of the atom consistent with the Octet Rule, starting with helium and expanding the model into neon and then argon. The noble gases have full outer shells of electrons and make good examples. We begin with a drawing of a positively charged nucleus as a small sphere. Starting with the duet rule and the n=1 shell, we can represent the first shell as a circle or sphere around the nucleus. Duet means 2. Our first shell is complete with 2 electrons. 2 dots are added to the first shell as a representation of the paired electrons. Notice the similarity between the model and the dot diagram of helium, with its 2 dots above the symbol. Expanding the model has us moving into rows 2 and 3 elements. Row 2, with its 8 elements, gets a shell that can hold up to 8 electrons. Note that we are adding the electrons in the same manner that we did in generating dot diagrams for atoms. That is, 1 per side and then pairing. This is because dot diagrams and the octet sketch are really the same process for visualizing outer shell valence electrons. As we see, there is a close similarity with the dot structure of neon. For row 3 and its 8 elements, we add a new larger shell, which can also hold up to 8 electrons. As with the second shell, these electrons are paired, and the pairs are placed as far apart from each other as possible. The outer shell electron arrangement matches that of the noble gas argon. There is a shell level pattern of 2, 8, 8 that represents full shells for the first 3 energy levels. In building dot structures for molecules, the objective will be to get an atom in the molecule to have a full outer shell of electrons. That does, however, bring up the point that the only elements that have a full octet or duet are the noble gases. What about the other elements? How do they get a full octet? Two important ways. One, sharing electrons, covalent bonding, as mentioned earlier. And two, forming ions, which can enter into ionic bonding. For this lecture, we will concentrate on the sharing of electrons. And when we invoke the Octet Rule, we will also be including the principle that in a covalent bond, an atom can count both shared electrons towards fulfilling the Octet Rule. That means for each covalent bond an atom enters into, it gets to count an extra electron towards fulfilling the Octet Rule. In the bonding overview lecture, we use that principle to reason the number of bonds an atom needs to make to fulfill the Octet Rule, given the number of valence electrons it has. We also need to note how many valence electrons are unpaired and capable of forming covalent bonds. Limiting ourselves to atoms that form covalent bonds, we can populate our table with common atoms and their dot diagrams. For hydrogen, it has one unpaired electron. It can form one covalent bond and can therefore add one more electron towards the fulfillment of the duet rule. 1 plus 1 is 2. Carbon has 4 valence electrons, and they are all unpaired. It can form 4 covalent bonds, which means it can add 4 more electrons toward the fulfillment of the Octet Rule. 4 plus 4 is 8. Nitrogen has 5 valence electrons, and 3 are unpaired. It can form 3 covalent bonds, and adds 3 electrons to its count. 5 plus 3 is 8. Oxygen has 6 valence electrons, and 2 are unpaired. It can form 2 covalent bonds, and add 2 electrons towards the fulfillment of the Octet Rule. 6 plus 2 is 8. Finally, fluorine. It can form 1 bond. 7 plus 1 is 8. Now we're ready to build a dot structure. Let's take a deeper look at the sharing of electrons and practice drawing molecules using this Octet Rule type of sketching. We will then compare this sketching method to that of using dot diagrams and pushing them together to combine atoms into molecules. That building of dot structures is covered in depth in the 2 Lewis structure dot structure lectures, the basic and advanced dot structures. In a covalent bond, atoms share 1 or more valence electrons, approximately equal. What exactly do we mean by that? Well, consider the molecule methane. 1 carbon, purple sphere, and 4 hydrogens, green spheres. We're going to construct a molecule in which the atoms in the molecule have a full outer shell of electrons and thereby satisfy the Octet Rule. To do that, we need to have dot diagrams and atom sketches for all atoms. The dot structure of hydrogen is 1 dot on top of the element symbol. We can add 1 dot to each of the green spheres to represent the single valence electron of hydrogen. For demonstration purposes, the dots are not all drawn on top of the hydrogen sphere. Not to worry, atoms do not have tops, so any pattern of dots that has the same number and pairing of dots is effectively the same. We're only changing the orientation of the dot diagram and not altering the purpose of the dot diagram itself. And then there is carbon with its 4 valence electrons. Carbon actually has 6 electrons, but 2 of them are in the inner shell. Inner shell electrons are not going to be involved in covalent bonding. We are not going to concern ourselves with inner shell electrons. The 4 valence electrons of carbon go around the second shell of the carbon atom sphere in the same manner as dots go around the carbon symbol. It is of utmost importance to recognize that covalent bonding is the overlap of orbitals that contain a single electron. We call that a half-filled orbital. We see that the orbital on hydrogen and each of the 4 orbitals on carbon have only 1 electron in them and can therefore participate in covalent bonding. Not all orbitals on all atoms will meet that criterion. Bonding occurs when a hydrogen atom with its one electron approaches the carbon atom at an orbital that only contains one electron. The two electrons pair and are drawn in the region where the hydrogen and carbon atom overlap a bit. This overlap region is an area where the s orbital on the hydrogen shares space with a complicated mixture of s and p orbitals of carbon. This mixture is called hybridization and is covered in the Advanced Covalent Bonding lecture for those who need to better understand it. Many students will be fine with this level of understanding. For now, we will just say that the electrons belong to both atoms and that there is an overlap of orbitals. They are sharing electrons. Keep in mind, though, that sharing means that each atom has the electrons for half of the time. It does not mean keeping the electrons in between the atoms as drawn here. We will demonstrate this point later in the lecture when we cover unequal sharing in the polar bond. Back to our model. The same sharing arrangement follows for the other three hydrogens in carbon. Each hydrogen makes one bond and the carbon makes a total of 4. The molecule formula is CH4. What makes this work is that in a covalent bond, each atom gets to count both electrons in the bond towards fulfilling the Octet Rule. Referring back to the ratio coming out of the Octet Rule, hydrogen has a full outer shell when it has 2 electrons. As can be seen, each hydrogen has a full outer shell of 2 electrons. And the carbon, it gets to count the shared electrons, and that gives it 4 pairs or 8 electrons in its outer shell. Covalent bonding is a way for carbon and hydrogen to achieve a full outer shell of electrons. Now, let's be clear that this counting of both shared electrons is just a way of arriving at the correct arrangement of the atoms in the molecule, and not the addition or subtraction of electrons. In other words, the counting of shared electrons is just an accounting mechanism to help us understand how covalent bonding works. Drawing spheres is a bit of a cumbersome way to display the distribution of outer shell electrons in a molecule. Most of the time, when students are asked to display the molecule with its valence electrons, they will be doing so with dot diagrams and not spheres. Now, there's an involved procedure, a multiple-step method for generating dot structures of a molecule, but not all students are required to learn that. For most students, the pushing together of atomic dot diagrams will be sufficient, and that will be introduced here. It is covered in depth in the basic Lewis dot structure lecture. And for those who will need to learn the more involved process, there's a separate lecture in this series titled Advanced Lewis dot structures. Be sure you know which level you are expected to be familiar with. Staying with methane, we begin our pushing together process by replacing the spheres with the element symbol and their proper dot structures. For sharing to occur, the atoms have to have an orbital with a single valence electron in it. That's not going to be a problem here. Still, the requirement for a single electron orbital is absolute. We can form our first bond by pushing the hydrogen with its single electron into one of carbon's orbitals having an electron. A second bond is formed by pushing a second hydrogen with its dot into a second carbon orbital having 1 dot. Do not try to jam multiple hydrogens into the same orbital of carbon. There is a limit of 2 atoms per bonding site. A third and fourth bond is also formed. Again, we are not forced to keep hydrogen electrons at the top of the symbol. We are allowed to move the pattern of atom dots around the symbol to get the pieces to fit together. The do-it rule and the octet rule still hold. That is 2 for hydrogen and 8 for carbon. Both atoms in the bond get to count the shared electrons. Let's repeat the octet type of sketching and the pushing together process using atomic dot diagrams for a polar covalent molecule. In a polar covalent bond, the electrons are shared, but not equally. The dot structure does not show whether a bond is polar or not polar. So we will construct dot structures with polar bonds the same as dot structures without polar bonds. And we might as well begin with water. H2O. We start using 2 dot diagrams of hydrogen and 1 of oxygen. Oxygen's dot structure is a bit more complicated. It has 2 single unpaired electrons and 2 sets of paired electrons, lone pairs. Since covalent bonding is the sharing of electrons, and that is the overlap of orbitals containing 1 electron, we'll be using the single unpaired electrons for bonding, and that gives us a pretty good idea of what the final structure will look like. Now, to create a bond, we need to bring the 1 dot or electron in one of the hydrogen atoms into a bonding or pairing position next to the oxygen. The pair is a covalent bond. Same thing is done with the second hydrogen. This pair is also a covalent bond. We should verify that bonding has led to the fulfillment of the Octet Rule and the Duet Rule. The oxygen symbol has 4 pairs of electrons around it. That is the full octet. 4 of the electrons around the oxygen are in lone pairs, and 4 are in bonding pairs. Looking at a hydrogen shows us that it has 2 dots or electrons around it, and therefore satisfies the Duet Rule. Additional examples are in the Lewis dot structure lectures. It's time to explore the underlying principles involved in deciding whether a covalent bond is polar or nonpolar. That nonpolar term simply refers to a covalent bond that is not a polar bond. Electronegativity will be our guide. From the definition of polar covalent bonds, we see that it is a sharing of valence electrons, but not an equal sharing. Polar covalent bonds occur when the difference in electronegativity between the 2 atoms is between 0.5 and 1.9. A quick review of how to get the difference in electronegativities will not hurt us. Let us use the oxygen-hydrogen bond as an example. Begin by going to your copy of the periodic table with electronegativity values and get the electronegativity for the 2 elements in the bond. Oxygen is a value of 3.5. Write that down. And hydrogen has a value of 2.1. Write that down. Remember that electronegativity is the measure of how much an atom wants the shared electrons. Oxygen clearly wants those shared electrons more. Now get the difference, as in subtraction of the 2 values. Start with the larger one, 3.5, and subtracting the smaller one, 2.1. For oxygen-hydrogen covalent bonds, the difference is 1.4. Textbooks with periodic tables containing electronegativity data will also provide a scale relating the difference in electronegativity to the type of bond. The scale shows 1.4 to be squarely in the polar covalent realm. Now we can get a deeper understanding of what is meant by unequal sharing of electrons in the covalent bond. Water will serve as an excellent demonstration molecule. In a covalent bond, sharing is about time. How long does each atom have the shared electrons? Despite how we draw the molecule, it is not about how close or how tight the electrons are to an atom's nucleus. We can make a cartoon representation of how the shared electrons in this selected bond move from one atom to another, but from the perspective of time. Oxygen, with its large electronegativity, will want and get the electrons for a longer time. Watch. The electrons spend more time with the oxygen than with the hydrogen. While true electron behavior is more complicated than this, the cartoon representation does highlight the point that sharing is based on time. A breakdown of the distribution of charge for each atom can be even more informative. Before getting to that, we should clear up what is meant by lone pair electrons. Pair means 2 electrons. Oxygen has 2 lone pairs. Lone pairs are defined as being valence electrons that are not shared between other atoms. These electrons belong completely to the atom that has them. Unequal sharing leads to an uneven distribution of charge, but does not change the net charge on the molecule. The net charge is a comparison of the charge from the electrons and the charge from the protons. We can demonstrate uneven distribution of charge with an accounting of the charges in a molecule of water. Specifically, the charge is due to electrons and protons. Looking at one of the two hydrogens of the molecule, we see it has a single negatively charged electron and a single positively charged proton, as does the second hydrogen atom. The oxygen atom has 8 electrons and 8 protons. Water must therefore have a total of 10 electrons and 10 protons. The total number of negative charges is the same as the total number of positive charges. The charges balance out. Water is a neutral or a no net charge molecule. Keep that in mind as we discuss redistribution of charge that accompanies polar covalent bonding. To better understand unequal sharing, we first have to look at equal sharing from a time perspective. Methane, or CH4, will do as an example molecule. In a covalent bond, the shared electrons spend half their time around each atom. Before we proceed, this notion of sharing by time, it is helpful to remind ourselves of the distinction between counting charge and counting electrons to fulfill the Octet Rule. In that rule, both atoms in the bond get to count shared electrons. Counting the same electron twice is just a way of understanding why bonding occurs. But each single electron in a bond is, after all, just a single electron. So when we are keeping an account of charge, we cannot count the same electron twice. Therefore, when counting charge in a covalent bond, both atoms in the bond get to count a fraction of the shared electrons. Adding that fractional charge from both atoms in the bond cannot exceed the number of electrons in the bond. The fraction must add up to the total number of electrons in that bond. How does this work out? Consider a covalent bond with two shared electrons that spend half their time around one atom and the other half around the other atom. Each of the atom counts 1/2 of the total shared charge. For each atom, that comes to 1/2 times 2 electrons for a value of 1 electron. But that should not be such a surprise, because 1 electron is what each atom brings to the bond. In the end, equal sharing just means that atoms get as much as they give. Another way of saying this, neutral atoms form neutral molecules. Covalent bonding does not change the net charge. This will hold for polar covalent bonds too, even though the sharing is not equal. Like polar covalent bonds in water, the shared electrons spend more time around the atom with the larger electronegativity, in this case oxygen. Oxygen gets to count more than 1/2 of the total shared charge. Not much more. We don't need to know how much more, just that it is more than half. We saw that in the covalent bond, multiplying 1/2 times shared electrons gives a net 1 electron. That keeps neutrality. In this polar covalent bond, the atom of oxygen will multiply more than half times the shared electrons to get more than 1 electron. Again, we do not need to be specific about how much more. That more than can be written using the more than or greater than sign. Importantly, the oxygen only brought 1 electron to the bond. 1 electron would make oxygen neutral, but its count from the bond is more than 1 electron. Oxygen will have more negative charge than it started with. It will adopt what is called a partial negative charge. We will get to that partial bit in a moment. The symbol for partial is the lowercase Greek delta. We can include a negative delta sign near the oxygen to signify that this side of the molecule has more negative charge than positive charge on the basis of time the shared electrons spend with the oxygen. We're not done though. In the polar bond, hydrogen counts less than half of the total shared charge. Less than half times 2 shared electrons is less than 1 electron. The less than sign can be used to show that. Importantly, hydrogen brought a full electron to the bond, but in bonding with the more electronegative oxygen, it shares less than that 1 full electron. So now it has less negative charge than it started with. Consequently, it will adopt a more positive charge. It will adopt a partial positive charge. Again, the Greek delta symbol for partial is used, but this time there's a plus sign attached. Since there are two polar bonds in water, both hydrogens get plus delta signs. As arranged here, the partial charge signs show that one part of the molecule is slightly negative and the other slightly positive. Now we're ready for the term polarity. It is a separation of electrical charge leading to an electric dipole. Dipole will be explained in a bit. Water is a polar molecule because there's a separation of charge. One side of the molecule is partially negative, and that's at the expense of the other side. Separated charge. To give some perspective, a partial negative charge is smaller than the whole negative charge on an electron, and the partial positive charge is much smaller than the whole positive charge on a proton. And while there's a separation of charge in water, no new charge was added to the molecule. With no new charge added, the net charge on water is 0. As shown earlier, water has 10 electrons and 10 protons. It is neutral. Charge in the form of electrons is redistributed within the molecule, resulting in one side having more negative charge, but at the expense of the other. This all takes place in a molecule with a total net charge of 0. That being said, there should be a relationship about the size of the partial positive and partial negative charges. When we add together the partial negative charge on the oxygen and the two partial positive charges on the hydrogen, it must sum to a net charge of 0. That is the only way for water to be a neutral molecule. This can be shown by returning to our accounting of the charge in water. This time, however, the redistribution of charge will also be included. That first hydrogen had an electron contribution of less than 1. We will change that to a less than 1. The second hydrogen also has a contribution of less than 1. Oxygen is a bit trickier, but we can argue that since oxygen brings 8 electrons to the molecule, and each bond it gets to count more than 1 electron, it will have a net value of more than 8 electrons. How much more? It's not important right now. A net partial negative charge is found on the oxygen by summing the more than 8 negatives with the 8 positive charges from its protons. A net positive charge is found on the hydrogen by adding its less than 1 negative charge to its positive charge from its proton. Same argument for the second hydrogen, partially positive. Yet the total negative charge, 10 electrons, is the same size as the total positive charge, 10 protons. Water has a net charge of 0 even though one side has a slight negative charge and the other a slight positive charge. That is what is meant by a redistribution of charge, not adding or subtracting charge, but moving it around the molecule. We'll wrap up the unequal sharing with the concept of dipole. Because water has a positive end, partially positive charge, and a negative end, partially negative charge, it has a dipole. Di means 2, and poles mean center. The north and south poles of our planet are magnetic dipoles. Dipoles are graphically shown with simple thatched arrows that signify that the bond has 2 separated charge centers, one positive, one negative. There are 2 such bonds in water, and 2 dipoles can be drawn. The arrows are aligned in the direction of positive center, hydrogen, to negative center, oxygen, with the arrowhead at the negative center. In the molecular geometry lecture, we will see that the dipole arrows can combine to an overall dipole for the entire molecule. The dipole is consistent with our definition of polarity in this context. It is the separation of the physical property, charge. Dipoles and polarity are important concepts in chemical reactions, chemical properties, and intermolecular interactions. It is a topic well worth understanding. Our next topic is multiple bonds. In our definition, the covalent bond has one or more valence electrons being shared. The multiple bond is where each atom brings more than one electron and makes more than one bond with the same atom. Yes, both atoms bring the same amount of electrons to the bond. Consider molecular oxygen, O2. It is composed of two oxygen atoms. The dot diagram of oxygen shows it to have 6 valence electrons. And let's tip that symbol with its valence electron dots onto its side so that its 2 unshared electrons are oriented in a manner that highlight multiple bond formation. Again, the dot diagram is just a way to hold the valence electron pattern in the 4 different orbitals. Compare the dot diagram to a sketch of oxygen in the Octet Rule formation. Same tilted orientation. We now introduce a second oxygen with the dot diagram tilted so that its unpaired electrons are facing the first oxygen. A second sketch is added with a similar dot pattern. Each oxygen has 2 unpaired valence electrons, which means that each oxygen can form 2 bonds. Each oxygen also has 2 lone pair of valence electrons that will not participate in bond formation. The covalent bond occurs when an orbital with an unpaired electron on one atom overlaps with an orbital with an unpaired electron in a neighboring atom. The multiple bond occurs when 2 or more orbitals on one atom, each with an unpaired electron, overlap with 2 or more orbitals, each with an unpaired electron, on a neighboring atom. The shared electrons are drawn in that overlap. For convenience, the 2 sets of shared electrons in this multiple bond are drawn one on top of the other, but we could have just as easily put them side by side. Real electron behavior is much more complicated, and as we know, the covalent bond is about spending time around both atoms. Multiple bond formation fulfills the Octet Rule. We can count the electrons around the oxygen on the right. 2, 4, 6, 8. And around the oxygen on the left. 2, 4, 6, 8. Both atoms count the electrons in the double bond. Molecular oxygen. We can show that the triple covalent bond is formed in a similar manner, using nitrogen with its 5 valence electrons. We start with a sketch of the atom nitrogen, having a similar dot pattern, and then bringing up a second nitrogen atom. Note that each nitrogen has 3 unpaired electrons. That means each nitrogen wants to form 3 bonds. Each nitrogen has a lone pair of electrons that will not participate in bonding. Bonding will occur with the overlap of 3 orbitals. 3 covalent bonds are formed. And that can be seen as a slight merging of the 2 atoms. Without going into any real detail, 3 sets of paired electrons are placed in the overlap, indicating that the 2 nitrogens share 6 electrons. While not necessary, we can move the lone pair electrons to the opposite side of the atom, because in principle, electrons try to stay as far apart from each other as possible. The lone pair moved as far away from the 3 sets of shared electrons as it can. Counting electrons around the atom on the right shows it to have 2, 4, 6, 8 electrons in its outer shell. The triple bond allows nitrogen to have an octet of outer shell electrons. Not surprisingly, there are also 8 electrons around the nitrogen on the left. Nitrogen, N2. The last covalent bonding issue deals with polyatomic ions. Poly means many, and the many is many atoms. Some covalent molecules have a net charge. That makes them ions. Like with atomic ions, in a polyatomic ion, the total number of protons does not equal the total number of electrons. There are too many polyatomic ions to memorize all their names, but most textbooks have a small list of them, like this one, that contain the ions that come up regularly, and students generally learn the names by exposure to them in the course of their studies. Still, an overview of the naming structure is helpful, and it can be found in the Naming Compound lecture. Most polyatomic ions at this level have a negative charge. That is, they have more electrons than protons. Many of these are oxygen-containing ions, such as sulfite, SO3, with a -2 charge, carbonate, CO3 with a -2 charge, and hydroxide, OH, with a minus charge. On the other hand, there are only two positively charged ions, more protons than electrons, that come up with regularity. And these are ammonium, NH4, with a +1 charge, and hydronium, H3O, also with a +1 charge. While polyatomic ions are atoms that are covalently bound to each other, the fact that they are charged means that they can participate in ionic bonding. Here is the base sodium hydroxide, NaOH. It is an ionic compound composed of an atom ion, Na+, and a polyatomic ion, OH-. There's more on ionic bonding involving polyatomic ions in the ionic bonding lecture. Recapping the lecture. In a covalent bond, atoms share one or more valence electrons more or less equally. These are bonds in which the difference in electronegativity between the atoms is 0.4 or less. Covalent molecules tend to have low melting and boiling points. They are relatively soft, non-conducting solids, and are generally insoluble in water. Covalent bonding is driven by atoms trying to reach an octet of electrons in their outer shell. Importantly, each atom gets to count all shared electrons. Remember that counting is just an accounting scheme. For polar covalent bonds, the atoms also share valence electrons, but they do so unequally. These are bonds in which the difference in electronegativity between the atoms is between 0.5 and 1.9. Polar bonds increase the solubility of the compound in water. We saw that sharing electrons is about how long each atom has the shared electrons. In the polar bond, the atom with a higher electronegativity has the shared electrons longer, resulting in that atom adopting a partially negative charge. The Greek letter delta signifies partial. The atom with the smaller electronegativity has a partial positive charge. In the polar bond, charge is redistributed, not added. Water is neutral, even though it has a dipole. In this context, a dipole is a bond that has a partial positive end and a partial negative end. Dipoles are an important feature in chemistry. The multiple covalent bond consists of more than one set of paired electrons. Each atom brings more than one electron to the bonding. And finally, polyatomic ions are covalent molecules that have a net charge. They can participate in ionic bonding. That completes this very busy and very important lecture. Covalent compounds are all around us, and so is their chemistry. Study what you have learned and review the patterns.